Hello students, and welcome back to the Quarantined Lectures. Dr. Heinz with you here as always. Today I wanted to take an opportunity to expand on our mechanics lectures that we did, I believe, work 3, with some stuff that we just didn't have time to talk about. So today I want to talk about the center of mass. All right, guys, so to start our discussion on center of mass, let's actually look here at this football, right? So this football itself, we would assume to be a single object, right? But if you actually think about it, this is made up of a whole bunch of different particles, right? There are particles here, particles here, particles here, particles here, etc. The force of gravity are acting on all of these points really at the same time. So instead of trying to break down, all right, what's the effect of gravity here? 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 What's the potential energy here versus the potential energy here, right? For example. Instead, what we're going to do to just simplify mechanics is we're going to assume that this entire ball is just one object. So how do we determine where the center or where gravity, right, what the center of mass is, right? That's what we're going for here, right? So let's put this aside. The center of mass is defined as a position, it is rolling. All right, center of mass is defined as a position that is the average of that system's mass, right? So from a practical standpoint, again, in the case of the ball, that would be really right here, right in the middle of the ball, right? It's the point that it's just a uniform point for gravity to act on. And this simplifies, of course, all of our calculations in mechanics. So for example, what I'm showing here, right? Simple bodies with uniform density will have their mass located at what we call the centroid. So what you see is you see a circle, right? Obviously in the circle, that would be right in the middle of the circle. The donut, very simply, just the same, right? So what we're showing is the centroid is that little dot there. We also have in the center of the square, the rectangle, and then in the triangle, it's kind of in the center-ish, right? But you get the idea in that what we can do from a gravity standpoint, if we're looking at the force of gravity, we can just draw a single vector down on that, okay? So how do we find the center of mass? Now, finding the center of mass on those simple shapes like we were just looking at is easy enough, but what if we were looking at some other system, like something we'll look at a little later actually, which is a non-uniformly packed truck, right? Like a truck that's like a moving truck that someone didn't do a very good job packing. How would we find the center of mass of that truck itself? So for complicated shapes or bodies and systems with a non-uniform weight distribution, we need a more universal formula, which is what we're seeing here. So what we can really do is look at the vectors of all the various parts, right? So again, in this case, if we were to break down, all right, what's the right, because we have these, so maybe we would look at the center of mass here, we would look at the center of mass of the ball, and then we would try and figure out exactly, because right, this is on top of the ball, so it might pull the center of mass a little upwards from the actual like center middle of the ball. Right, so what we're going to do is we're going to just look at, we're going to do vector addition of all the weighted positions. So center of mass X, center of mass Y, and then together these give the coordinates for the center of mass. And functionally what we're doing here, right, if we really break it down, what you're looking at is M times position, mass times position, mass times position, mass times position. Okay, so let's put this functionally in looking at this. So let's look at the case below where we have a small mass connected with a weightless rod to another larger mass, that other larger mass being M2, right? So it functionally makes sense to us that if we were to find the center of mass of this object, that it would lie closer to the larger mass than it would the smaller mass, right? Because it's weighted, right? For lack of a better term. So the equation that, because there's just two here, the equation that would do the X location of the center of mass would be M1 X1, so the mass of the first one times its position, plus the mass of the second one times its position divided by the total mass, right? And what we're going to end up finding is that it slowly skews. So you also notice here that we have the lines drawn. So I wanted to make it clear here that you can use a reference position as well. It would have been, potentially very easy here to put the reference position also on the small mass just to make it 0. However, it makes more sense I wanted to show the more general case of having some other reference position. Okay, so let's do an example problem, okay? So 3 weights are added to a straight rod with no mass as shown. Find the center of mass of the object. Okay, so how we're going to do this, now functionally we know that it's going to lie somewhere in between the 30 kilogram weights, between the two 30 kilogram weights, right? Because it's going to pull that distribution over away from the 20. Okay, so because all masses are on the same axis, we really only have to use the x position here, which is fine. So it's m1x1 plus m2x2 plus m3x3 divided by the sum of the masses, which is 20 plus 30 plus, well, 30 times 2 plus 30 times 4. So because that's 0, 60 plus 120 divided by 80. So it's at 2.25 meters, which means that it's 2.25 meters away from the small weight, right? And this is the case of, like I was talking about before, where we actually just set the small weight as reference 0. You could very easily have gone from the other side calling it 0, and what we would have found in that case was that it was 1.75 from the larger weight on the end. All right, so now let's move looking at combinations of objects. This is kind of the next step. So if we were to lay this out in a grid, right, say a system's made up of 3 masses at xy locations as shown. If we wanted to find the coordinates of the system of mass here, we can just do something very similar to what we've already done, but in this case we have to look at both the x and the y because we're not on just a single line. Okay, so if we do the x, we look at, you can see this guy over here and the 1 kilogram here and the 2 kilogram up here, right? If we find the locations of their center of masses, that's what we're using. So in this case, it's 2 times 5, right? Because it's a 2 kilogram block, times being at x location 5, plus 2 times 7, right? X location 7. And then the 1 kilogram ball is at x location 11 for its center of mass, divided by 5, which is the total mass, and what we end up with is 7. Now for the y coordinate, we do 2 times 3, again, that's 1, 2, 3 up, plus 2 times 12 all the way up, and then again the 1 kilogram ball at 5, 1, 2, 3, 4, 5 up. So it's 6 plus 24 plus 5 divided by the total weight, which is 5, and we get 7, which means that the center of mass of this entire system here is located at 7, 7. All right, so a relevant example of where this might be is, like I said, like we talked about earlier, which is determine the center mass of a poorly packed truck. And then what we'll talk about in our next lecture is functionally, what is the tipping point, right? Why do we care about the center of mass? Is because it helps us determine not only the effects on the object itself, but how stable that object can be. So that's what we'll be talking about on the next example. If you have any questions or anything like that, please leave them in the comments below or reach out to me personally. If nothing else, thanks for joining me.